to the Journey Shake Chem. Today's warm-up is one from one side of the worksheet and one from the other side of the worksheet. I know you can do it. Do the best you can, and we'll see you in a moment. In number one, we are given the value in grams, and we are solving for volume of the carbon dioxide. And first, I must always get a balanced equation. And this is one of my most famous decompositions of a metallic carbonate. And the common molecule I get out of that is carbon dioxide, and then I'm left with my magnesium oxide. Now, I change my grams to moles, and oftentimes, students are unsure of how they should start. And the unit that you're starting with will oftentimes tell you where you need to start, because in order to change my grams to moles, I need the atomic mass unit or the gram formula mass from the periodic chart. If I put the volume down here, that would not cancel. My unit would not cancel. So if I look at what I'm given, and I always have to have that long line there for that big conversion, then it tells me that I'm going to need the AMU in the bottom in order to go to moles. And 1 mole of magnesium carbonate, well, magnesium has a mass of 24.3, and carbon has a mass of 12. And 3 oxygens is 3 times 16, and that is 48, and 12, and 24.3, and the sum of that is 84.3 grams per mole. And by putting the grams in the bottom, I then can cancel. So that step gets me to moles. And then I use the mole ratio from the balanced equation. This one's nice because it's a 1-to-1. There is 1 mole of carbon dioxide for every 1 mole of magnesium carbonate. And then I must go to volume. Now, the question did not specifically say what unit of volume I needed. So I'm just going to go to liters or decimeters cubed. And I know that there are 22.4 liters of carbon dioxide in 1 mole of carbon dioxide. And therefore, if I do the math, I get 3.5871. I look back to my original problem, and I need 3 significant digits, and therefore my answer, I look at the 7, it rounds the 8 up, 3.59 liters of carbon dioxide, or 3.59 liters of decimeters cubed, or liters would be interchangeable there. And that's how you do number 1. In number 2, the balanced equation will be a type of combustion. And we're given butane, which is C4H10, and in order to burn anything, oxygen is required, plus oxygen. And then the products of complete combustion, which is what we always have is complete combustion, we always get carbon dioxide and water. Now, when I try to balance this, I see I have 4 carbons here, and therefore I'll put 4 as a coefficient in front of my carbon dioxide. I need 10 hydrogen, so I will put a 5 in front of the waters. Now, because my oxygen is by itself, I can manipulate the numbers of oxygens. Therefore, I look, and here I have 8, and here I have 5, so together that gives me 13 oxygens. Well, that's an odd number, and any number that I use, I'm going to multiply by 2. So I'm going to start out with a fraction, and then that would balance it. Now, I cannot leave it in fraction form, so I multiply everything by 2. And therefore, I have a 2, and 13, and 8 carbon dioxides, and 10 waters. And that's a little bit of review from balancing equations on how to balance one of these combustions that don't come out with an even number. Now, I'm going to use this balanced equation, and what I'm given in the problem is 1.5 meters cubed of my butane. And what I'm looking for is the oxygen. It does not matter if the unknown is on the product side or the reactant side, the relationship will remain the same. Now I'm going to take my 1.5 meters cubed of my butane, and because I love drawing that line, because I'm going to use my standard molar volume, which is in decimeters cubed, I'm going to go ahead and change my meters cubed to decimeters cubed so that my units cancel properly. And I know there are 1,000 decimeters cubed in 1 meter cubed. And then I'm going to go ahead and change my meters cubed of my butane to moles. And 1 mole of butane, C4H10, is 22.4 decimeters cubed of the butane. And then I use my mole ratio from the balanced equation. And I have 13 moles of oxygen for every 2 moles of butane. And then for moles, I go back to volume using standard molar volume. 1 mole of any gas is 22.4 decimeters cubed of that gas. And when I do the number here, it comes out even. And I could put zeros there to show that it came out even, but then I'm going to round to 3 significant digits, and therefore the number will be the same, 9,750 decimeters cubed of oxygen. And that's how you do number 2. You know how excited I get when we're starting something new. Well, today we're going to talk about the ideal gas law. Yes, the ideal gas law. Well, what you might want to do is take a look at the sheet that you have that has the equations for gas laws part 1 and gas laws part 2. And refer to that. You'll need some of the numbers that are on the back of that, the vapor pressure of water at different temperatures. And that will give you the standard pressure values that we will be using. Now, the ideal gas law is PV equals nRT. And some teachers call it Pivner. But I don't call it Pivner. I just call it the ideal gas law. Now, it does include P is for pressure, V is for volume, N is for moles, R is the important one that we're going to discuss, ideal gas constant, and T is for temperature, which is always in Kelvin for gas laws. Now, I need to know what this ideal gas constant is, so I'm going to solve my equation for R. And therefore, R equals PV. And to undo this multiplication, I'm going to divide. And therefore, R equals PV divided by NT. Now, obviously, we have lots of different values for pressure. And you do not have to memorize what R is because you can solve for it whenever you need it. You probably will remember some of them because you'll be using them so often. But in case you forget, you can always solve for that R. Now, we're going to solve for R together using standard values with kPa. And standard pressure in kPa is 101.3 kPa. Now I'm going to use standard molar volume. And if you recall, standard molar volume means that 1 mole of any gas under standard conditions occupies 22.4 liters. And therefore the volume would be 22.4 liters. And that would be 1 mole. And the temperature would be 273 Kelvin. Now we want to give all of these constants 3 significant digits. And therefore when I do the math, I have 8.31. And now look very carefully. We have a complicated unit. It's not really that complicated. It's just that moles and kPa, they are not divisible because they're different. And just like only the same numbers can be divided, the same units can be divided as well. So what we get here is kPa, liters per mole Kelvin. That's the unit here. That's quite some unit, isn't it? It's very complicated, but it's not really complicated. It just makes you look like you think you're complicated. But in any case, the critical part about following through with our units is that when we have a problem, for example, and we're given milliliters, well, then I would have to change it to be consistent with my liters to put that value into the problem. So I have to be consistent with the units that are in this ideal gas constant. Now, the first side of the worksheet C that you're going to do is you're going to solve for the ideal gas constant with different units of pressure. And you can obviously see if I have a 1 here instead of a 101.3, I'm going to come out with a different number. And that's what you do first, is solve for those various R values. That's what you do first, and then we'll talk about it a little bit more in a moment. The ideal gas law allows us to solve for a variety of different values, including the ones that are in the ideal gas law. Well, we know that our ideal gas law is PV equals nRT, and we can solve for any of these variables in that law. Now here I'm going to talk about N, and N is equal to moles. Well, what are moles? I know you're going to say that furry little beast that goes in those holes, but that's not the one I'm talking about. I'm talking about the one that's Avogadro's number of particles. Well, moles is equal to the number of grams over molecular weight. I use MW for molecular weight, and oftentimes in some textbooks you'll just see a capital M. We have so many capital M's in chemistry and math that I like to use the MW together to represent molecular weight. And that's very helpful, I find, when I'm rearranging the equation, which is exactly what I'm going to do here. Well, if I know that moles is equal to grams over molecular weight, I'm going to put that into this value for N. And therefore, we will have PV equals grams RT over molecular weight. And so you can see how now I can solve for molecular weight. I multiplied to get it out of the denominator, and therefore molecular weight times PV is equal to GRT. And I want to isolate molecular weight, and therefore molecular weight is equal to GRT over PV. So we can solve for molecular weight, and we're going to do this in one of the labs. You'll have an unknown volatile liquid, and you'll determine what its molecular weight is, because we will know its mass, we will know the temperature of the boiling water, we'll know the barometric pressure, and we'll know the volume of the flask. So we'll be able to do that in the lab and get an experimental value. Now there's one more thing I can find here, and if I look, I can see that I have density in this equation. Density is mass over volume. And all I have to do is remove the other things that are around it. So I isolate that mass over volume. And therefore, molecular weight times pressure divided by RT is equal to grams over volume, mass over volume. And when I solve this, I will get one number for this density, but the unit will be grams per liter or grams per milliliter. I will get a unit for that number that reflects the mass and the volume. And so we can solve for molecular weight, and we can solve for density using the ideal gas equation. Well, I know you can do this, no problem, so just do the best you can, and your facilitator always goes over the assignments with you that you had the night before. And then you have practice. And that was some fun, and thanks for being here, and I can't wait to see you tomorrow.